All right, so in the next video, we'll take a look at some other math review type topics. And one of the main things that we need to be able to do is to interpret graphs and also generate graphs, which is an exercise you'll be doing in the next lab period. So let's take a look at how we can interpret graphs and represent or show relationships between different things using a graphical format. So when we look at graphs, they are efficient ways to show the relationships. So for example, if we wanted to show how the prices of, let's say, homes have changed over the course of time, on the x-axis on our graph, so we have two axes, an x and a y. The x is the horizontal axis, the y is the vertical axis. On the x-axis here, we typically have labels associated with the axes to show what is it that we're actually plotting. So here we're going to have year, and let's say we're going to start off with let's say 1980, 1990, 2000, 2010, 2020. And then on the y-axis we have the, let's say, the median price of a home. And this would be in dollars. All right, so we'll have, let's say down here, we'll have 20,000, we'll have 40,000, 60,000, etc. And what we find is that over the course of time, maybe back in 1980, the median price was about maybe 10,000, and we got to 1990, it was maybe about here, about 40,000. In 2000, it was up to maybe about 80,000, etc. So once we plot those data points, we can connect them now, and we can see that there's a relationship between, or we can see how the price of a home changes as the year passes. So we can say that the price increases, or the price increased as the years go by. And that's a very simple example of a relationship we can deduce from the graph, and it's very easy to see that as opposed to you being presented with a bunch of numbers, right? So graphs are good visual ways to represent data. So in the examples that we have here in the questions, it's saying, well, choose a best graph that shows the following. So time climbs down a ladder from the roof, and in our graphs here on the x-axis we have time, and on the y-axis we have the distance above the ground. So think about what's going on. If this person is climbing down from the roof, that means as time goes by, on the x-axis, their distance from the roof should decrease, right? They're getting closer to the ground. So we may start off with a high distance from the roof, and then as they climb down from the ladder, the distance from the above the ground decreases, and then eventually they get to the ground, right? So we see that there's this line here that slopes downwards that shows that relationship. Similarly, if we're saying that we're looking at a person walking with a constant speed to the store, right? And we're plotting the speed here on the y-axis and time here on the x-axis. If they're walking with or moving at a constant speed, that means the speed is not changing, right? So this stays constant as time passes by, and our graph here is going to look like a straight line, a horizontal line going from left to right. So the idea behind these questions is just to get you oriented with how graphs look, how we interpret them, And then in lab next week, we're going to be collecting some data and actually drawing graphs on your own. All right, next couple of questions. We're going to take a look at using and representing numbers in scientific notation. So the first one here, we have a number provided, 0.6415. That's a regular decimal number, decimal notation. We want to convert that to scientific notation. And when we write a number in scientific notation, there are a couple of things we need to keep track of. First thing is that the format of the number is going to look like this. So we're going to have this number written here that we call a coefficient. And this coefficient has to be a number between 1 and 10. And that's multiplied by 10 raised to a certain power. And that can be either a negative or a positive power of 10. So if we're provided with our initial decimal notation to begin with, there's our decimal point. We need to move that decimal point in a particular direction, either to the left or to the right, to give us a number between 1 and 10. In this case, we'll move the decimal point to the right one place. And we end up now with 6.415. And because we had to move the decimal point to the right, our exponent here is a negative exponent. We moved it one place to the right. So we end up with 6.415 times 10 to the negative 1. And the way that we can check our answer is by looking at this, the power of 10. If you have a negative power of 10, that means the number is very small. All right, which is going to be less than 1. If you have a positive power of 10, that means the number is large. When we have numbers in scientific notation, we're going to have to work with them, enter them in our calculator, and express our answers using scientific notation as well. So it's important that you are able to use your calculator effectively to enter numbers in scientific notation. Okay, and in most calculators, we can enter the numbers as written or as we have them written here. I would encourage you to make use of the parentheses to separate each of the numbers written in scientific notation. So keep in mind that if you open up a parentheses or parenthesis, you need to close it at the end of the number, and then you can have your multiplication sign, open another set of parentheses, and then close it at the end, and then we hit enter at the very end of this. As we start making measurements and doing calculations, we're also going to have to be able to round our numbers properly. So we'll take a look at rounding really quick. So we have a number shown here, 38.721 grams. And it says that we need to round this to 2 significant digits. 2 significant figures, SF. So what we need to do is to apply the rules for significant figures. First of all, recognizing significant figures. And we're going to start at the left side of our number and work our way across this way. So remember the rules. Any non-zero digits or any non-zero digit is significant. And then the zeros are where we need to pay a little closer attention. So for the zeros, zeros at the front, which are called leading zeros, those are not significant. If we have zeros in the middle, between, they don't have to be exactly in the middle, as long as they're between non-zero digits, are significant. Sometimes you'll see that being referred to as confined or sandwiched zeros. So those are significant always. And then the zeros at the end of a number. So those are called trailing zeros. These are significant only if there's a decimal point in the number. And if there isn't a decimal point in the number, then they're not significant. So if we take a look at our number that we have, starting on the left, we have this 0 here. That's a leading 0. That's not significant. So our first significant digit is this one. That's a non-zero digit. That's a 3. Our second is the 8. So we're going to stop right about here. We look at the next digit. Is it 5 or above? It is. We're going to add 1 to the previous digit. So that ends up being 39. And then grams is our unit. So that has 2 significant figures or significant digits. So recognizing sig figs and rounding is one part of the concept. The second is actually applying the rules of sig figs when we perform mathematical calculation. So for example, adding and subtracting, we use one set of rules. For sig figs, when we multiply and divide, we use a different set of rules. So we'll just quickly remind you of those rules. So multiplication and division, the rule is the final answer can only have as many sig figs as the number with the least number of sig figs. And when we add or subtract, the rule is the answer can only have as many decimal places. As the number with the least number of decimal places. So in this case, we are doing adding and subtracting. So let's do the middle one here. So we have 18.9 grams plus 1.020 grams. And the way that I like to do this is I like to rewrite my numbers and line up the decimal points. That way it's going to be a little bit easier to see. When I add these and I stick it in my calculator, for example, right, I'll get 19.920 grams. I can then draw a line right after the number with the least number of decimal places. So that's the 9. That's 1 decimal place. So then our final answer can only have 1 decimal place. So we're going to round that. The next digit here is a 2. So that's less than 5. We're going to keep the previous 9 as it is. So this ends up being 19.9 grams as the final answer. So you want to make sure that you use the correct rule for the correct type of operation that you're doing. All right, and then the next one looks at making measurements, which you had a little bit of practice of or with in lab. So you can actually see a magnified view of this. So if you zoom back out, we can see that and I'll draw it over here as well. So we have 80, we have 100, and then we actually have smaller graduations between the 80 and the 100. We have, let's see, 1, 2, 3. So we got this one, got a bigger one, we got another one there. All right, and then our meniscus, if we look at where the liquid is, it's right about at the first line there. Okay, so in this case, my smallest graduation that I have, if I go midway between 80 and 100, that's 90. And then midway between 80 and 90 would be 85. Right, so reasonably, what we can estimate this volume to be would be dictated by the smallest graduation. So here the smallest graduation is 5 milliliters. How much can we reasonably estimate between the 5 mils? Well, reasonably we can say plus or minus 1 milliliter. So that means if we have a volume in here, we can say 81, 82, 83, 84, 85, etc. If we think it happens to be exactly on the 85, we can then say 85 mils, right? Where the 5 here is going to be our estimated digit. All right, and then the last question looks at a metric conversion. So it says down here that a chemist measures the mass of an element. The mass is 56 pg, and then it says, what is this mass in grams? Which is g. Okay, so the pg over here, this is a metric prefix that stands for picograms. So P for pico, G for grams. And pico is not one of the prefixes that you need to memorize, but it is one of the metric prefixes. So this one you can actually look up in your textbook to see what the relationship is between picograms and grams. And then we can use that as a conversion factor, the same way you would use any other relationship as a conversion factor. All right, so for example, we can see that 1 gram is equal to however many picograms, right? And you're going to look that up in your textbook. We can take this and we can use it as a conversion factor, and we can express it simply by putting one side of the equality over the other side, or we can just flip it to get the other conversion factor. And we can take either one of these conversion factors and we can insert it into our calculation. So if we're starting with 56 picograms, you put that over 1. If we want to end up with grams as our unit, we're going to take the conversion factor that has grams on the top, and then whatever you find for picograms here on the bottom, that's what you put on the bottom because you want the PG to cancel out. We end up with grams as your unit. Okay, so when you look through the videos for this chapter, you will see that there are several metric prefixes that you need to memorize. Those are the ones that are most common, so make sure you know those. Pico isn't on that list, but it is still something that you can look up in your text, right? You'll find it in your textbook. You can quickly Google it if you want. The idea behind this question is to have you use that relationship to perform the calculation, right? So to incorporate it into this conversion factor. So the technique here is the important thing, because we'll use conversion factors and dimensional analysis not just this week, but the subsequent weeks in the semester.